Okay, let's talk design of wall footing briefly. This is simpler than the design that we see for square footing because this is one-way situations. It's like we're designing one-way slabs and the problems are given right there. We have a net bearing pressures over there and we have a concrete strengths and also we have loadings and everything. Okay, and this lever yield strengths and I'm gonna start first of all preparing a loads for calculating the area, foundation area. Foundation area can be calculated by dividing the vertical load by the bearing capacity. All right, the vertical load right there is a unfactored, as you know, right? This is unfactored. Okay, unfactored. So you don't multiply load facts when you estimating a area. So we want to go a service road to calculate area, but area will be revised later for design of levers and thickness of the foundation anyway. So we have 140, 180 and go here without load factors and we have a 240 for bearing capacities, but we need to subtract a load already existed on the foundations, which is the wall and soil weights and the weight of the foundations, right? In this case, we don't consider the surcharges. But anyway, the soil bearing capacity reduces to 210 after we subtract all this load which already exists on the foundations. And we come up with a 210 so that we have a this much area needed, assuming a 1.6 of foundation width, because this is a one way, right? This is one way. So assuming 1.6 foundation width, then the total net bearing capacity can be calculated using 1.6 square meter per meter, right? So per meter, don't forget this is square meter per meter per meter because we are assuming the width of the foundation first of all here, okay? So, and with the foundation width of 0.16 meter, we come up with a fact. Okay, now we use 1.6 meter square per meter, which is meter, right? So this is a assumed foundation width based on this value, AP. Okay, so now we are ready to calculate. I'm gonna erase out of here. Let's say, can I erase this? Okay, good. Okay, great. So here I see a factor net bearing pressure. This is not capacity, okay? This is bearing pressure. Pressure, isn't it? This is pressure, okay? Not capacity. So we calculate factored net bearing pressure using a factor right here. Factor, okay? Here and here. Okay, 1.2, 1.6 for dead load and live load respectively. And we end up with 885 kilonewton per meter squares of varying pressure. This is the pressure which acts upward on the foundations, and we need to design all the reverse and concrete thickness and whatever against to protect the foundation against this pressure. All right. Okay. Now I'm gonna go a little faster because this is a easy part after a secure design, and we need a critical failure region, which is D from the the column face, which is D away from the column face, and right there, so that the shear load acting on this area will be subjects the foundations on shear force. Okay, so we have a shear loads on the critical or effective area right there. This is D from the base of the columns, and this is a strengths, nominal strengths and design strengths of the foundation, and we compare this. If this is not okay, which is not okay right now in reality, then we have to go and increase foundation depths again right there, so that we repeat all the same calculation again and make sure that we are okay with the shear capacity, which is provided by only on the depth of the foundation. And we go and calculate the fractional design, which is based on moments that acts on the foundations. And when you calculate moment, we have to consider from the face of the column, as I said, from a two-way design case, and we're going to have this length is obtained for the span of calculation of fractional moments, and we use this formula to calculate a fractional moment, which is 60.2 kilonewton meter per meter. We are considering a loads on 1 meter distances right there. So this is a moment from which we can calculate area of Libaras, and very easy, and this is not a big problem. And we have a minimum areas given by this, and everything's okay when you select this area for Libaras, right? And this is summary, right? We have assumed, and now we calculate 1,600 millimeters, and with depth was increased, revised to 350s, and we have a reverse, and this rebar goes one way right now. Okay, one way slab, and we may have to select another longitudinal slabs for temperatures and for unstructural reasons. Look at that right there. But this is not the rebar runs through the longitudinal direction. It's not for structural. Structural is transverse directions. This is rebar for a structural moment, reduced structural bending moment, isn't it? And we have a cover required is 75 millimeter, and this is what we have as a result of foundation design for wall foundation design. Now here, let's take a look at design of rectangular foundations. This is a little bit, everything's all same with a square foundation, but there's a couple of things that we need to understand what is different from the square designs, right? Okay, all the same up to calculating moment that acts on the foundations, acting on the foundations, and we come up with a levers again. This is all same, and we calculate and compare them with the minimum lever required by the code. So this is a minimum required by code, which is 0.0018 and BD, and we need to choose this value to design a lever. So we chose a 12 number 25 bars will be satisfying this value. So now the problem is how we're going to place on the rectangular foundations, and we can just place rectangular foundation in transverse direction evenly. Okay, evenly means all the way with equal distance this directions, right? But this maybe not okay, because if you take a look at column locations there, this column, let me just erase this. I mean, if you see column locations, and columns are right there in the middle of foundations, and the slabs near the foundations or near the columns will be subjected to severe loadings instead of the portion which are away from the column right there. Okay, so we can think of doing something else, because we want to add more levers at at this locations where in the vicinity of column locations. And we have to calculate this distance, and this distance is called a middle strip in this particular design case. The middle strip is a half of 1500 and half of the strip here 300, half of this 1500, half of their 1500, right? So middle strip becomes a 3 meters right here. So we have a 3 meter and middle strip here 3 meters. And in here, we want to concentrate transverse rebars. And then we're going to place the rest of the rebar outside of the middle strip. Simple, isn't it? Why? Because we would like to see this middle strip is more severely subjected to the loading because the column is near, right? Okay. So how then you calculate amount of rebar that should be placed in middle strips is easy. You calculate beta. Beta is the ratio of long side and short side. So it is long side, 4, short side, S3 a meter, which is right there. And you get this much and times total number of rebars, which is 30, you get a 25.7 rebars must be placed in column strip, as you see over there. Let's take a look at 26, and we're going to go 2 here, we're going to go 2 here, so that we total anyway, we're going to use all 30 rebars, right? So the 20 rebars and the middle strips and the rest of the area receives the rest, which is 4 and 2 and 2 shared. Okay, so this is easy. So this is what we're going to end up with the rectangular footings. Okay. Okay, now we can take a look at combined footing as explained earlier. This combined footing has prepared when you have a property line out there. You can proceed further because of the property line, and you may have some problems to design loading coming through the columns near the property lines, right? So what we have to do is then we have to extend the foundation in the other side of the foundation, and we put another columns over there so that we can balance all the load on the foundations properly. All right, so this is a one columns that we have to extend it the other way to take care of the column near the property lines. All right, this is called a combined footing. And combined footing treat like a continuous beams, continuous slabs. If you remember, this is a normal slab or continuous beams, and this is a bending moment diagrams. Okay, here according to these bending moment diagrams, we need a lever right at the top of where we have negative moments, and we need the lever in the bottom of the section where we have a positive moment, right? So I prefer drawing bending moment diagram this way instead of this way. A lot of people has their own way plotting bending moment diagram with different sign conventions, but I strongly recommend you guys to draw the bending moment diagram looking like this. All right, so positive in positive, negative is located in negative region of the cross, and easier to see where we have to place the levers according to the sign conventions, right? So this is a reversed slab. It's very simple to draw the bending moment diagrams here. So this is should be like this. If you flip over this one to look like a slab, then you're gonna have this, right? And you just go and flip over the original locations there. Then you're gonna have this, right? So this is easy to understand why the bending moment diagram should look like this. Okay. And here then, one thing you know that we're going to have a, look at here. This is now negative moment, right? This is now negative moment, right? according to design conventions here. Very confusing, isn't it? But you can just think everything in opposite directions, right? And this is a positive right now for foundation can be negative, and this is positive. Negative for foundation should be positive for slabs, right? So this is positive becomes negative, negative becomes positive, and negative becomes positive, and so on and so forth. So this is the reversed diagram for foundation, but they are same diagrams, right? Okay, so we have a top reinforcement and top reinforcement, although you're in the bottom reinforcement, right? Yeah, I think this diagram from the literature that I'm taking from our textbook, McGregor and the book there, Prentice Hall. There we need a horizontal reverse right there. Okay, it's missing from the textbook. Okay, we're gonna help them to fix that. And this is the rebar configurations that we have to place. Right? And actually, you don't have to go right there because this is a bottom rebars corresponding to this moment, bending moment diagram. But we just extend it to the end. But to me, it's kind of minor error occurred right there. The author somehow extended this to replace this reverse, but it's not. So we just follow the mechanics, structural analysis principles. Then this rebar should stop somewhere here, should stop somewhere here, and this rebar should be one on there as a revision. Same thing here. So this is top, right? This is top because this is a moment, negative moment or positive moment or whatever according to the definition. And yeah, what about here? Yeah, this is this portion, is it? This is this portion. So okay, let me see the bending moment diagram at cantilever part. This is cantilever part of the foundation perspectives. Okay, so this bending moment diagram should go and end up like that, right? Okay, it can go to further here, right? It should go in, and if you have a cantilever right there, it goes end up with the zero bending moment, right? So we have to go end up with the zero moment right here. So, and this portion of the cantilever slab should have a top bar continued, right? Right there. It's like the top bar continued right there, okay? And this top bar should continue like that. Okay, this is what happened at cantilever portion of the combined foundations. So this bending moment diagram should go and end up with a zero, not with some values up there, right? So you should be very careful to draw the bending moment diagrams. The bending moment diagrams are easy to plot, right? It's a little bit requires your attentions, but it's easy to draw the. For example, okay, this is another example. Another example for strap or independent foundations. And again, this is your cantilever and this is your cantilever, right? So your bending moment diagrams goes like this, and you need to place your rebars at the bar face, which is top face for slabs, right? So this is another one that we saw before, and that's just try to help you one more time with the bending moment diagrams, and you have a loading on there. So bending moment diagram goes like that. Your bending moment diagram goes like that, right? Something like that. Okay. Your curvature may be different, but the direction of bending moment diagram. Let's take a look at the only direction of bending moment diagrams. Okay, let's take a look at brief example review for combined footing. And combined footing is a quite complicated than the one we see with the strip footings and wall footings. Okay, let's take a look at it. And we have loadings here, and we have loading information for exterior columns and interior columns. and this live load, dead load, live load, all are given with the allowable soil bearing pressure. Okay, and also we have a surcharge loading by basements and the concrete and all that. All this information is given. Okay, so we don't have to worry about. Now we're starting calculating again the net soil bearing capacity. So net soil bearing capacity, original net soil bearing capacity is given by the soils report, right? And we subtract whatever existed over there, which is by the concrete or soil loads on the top of foundations, and also we have to subtract surcharge what is on there already. Okay, now we end up with this value 208.6 kilonewton per square meter as a net bearing capacity, which is available to the engineers and to the foundations, right? And we need to calculate required area, and then when you calculate required area, we need to know the vertical load, right? And this is a unfactored as well. So just you add a service load right there, unfactored load, and divided by the calculated and the net bearing capacity right here. You're gonna go put them right there, and with your total area you may expect to have for designing this combined footing. And here you need to calculate the load center. Our load center is based on your external columns and internal columns, and this is the distance from edge of foundation to external columns and internal columns. And this is very easy from a configuration of the foundation. Let's take a look at here. And okay, let me do it the other way. Look at that. Okay. This is a the distance for external loading and distance for internal loading, and from there you calculate load center. All right, that's easy. Okay, and the load center was calculated as 3,794 millimeter, and it is okay to assume the length of the combined footing is twice of this load center for just assumptions to start with the design. All right, you don't need much more sophisticated analysis for determining the length of the combined footing. Okay, we will just go and take twice of this value, which will give us a 7,600 millimeters. So what is then the width required to meet the area I calculate right there? We just simply divide this value by this value, right? So that we need this much width of footing to come up with a required area right there. Okay, so this is what we're gonna start with as a initial footing size. Okay, now we have an initial footing size, then we can calculate the net soil pressure. Right, net soil pressure means how much pressure is acting on your foundation. Now, this is the enemy, isn't it? This is not a friend. This is the enemy. All right. So in that calculation, we need to consider safety sort of factor. Safety sort of factors, which is provided by the load factor 1.4 and 1.7. So that your load pressure on the foundation is 309 kilonewton per square millimeter. Right, this is what we're going to have to carry out to design the depth of the foundation and the lever of the foundations. Okay, I'm not going to go through the construction of bending moment diagrams and shear force diagrams, but this is quite a simple thing to do. Call your structural analysis class. So this is a bending moment diagram as I gave you the concept, right? Goes here and goes like that. So this area, so if you see the normal slabs like that, you go like this, right? You go like this, you go like this, and you go like this. So here we have a top bar, which is bottom bar in foundations, right? Which is bottom bar here, top bar, which is bottom bar in foundation, right? This area. And this is a bottom bars for slabs, which is top bar for your foundation, this part, right? And this is, if you're confused, then you can just take a look, flip it over and take a look at it as a slabs and flip it back to original foundations. And this also, if you remember shear force diagrams, you can get a shear force at here, right? Shear force diagram goes like this, right? And we have a shear force diagram like that, right? And we have a little bit of skewed line over there because your loading is acting on the face of column pad or column body. Okay, but basically the shape of shear diagram is from this theory, which you learn in structural analysis course. Okay, so you are strongly recommended to calculate this shear force diagram and moment diagrams. All right, and you can calculate all the value corresponding to the locations importance. All right. Okay. Now then, we will take a look at how to design a rebars and AG. So rebars are designed based on one-way beam theory with a given B and D's and all that. You can calculate a rebar area. All right, that's all right. And here we have a same thing for three foundations. We have two-way shear situations. We have a one-way shear situations. So two-way shear situations are exactly identical to what we saw from three foundations. We calculate a shear force on the effective area. It is outside of a critical section, so-called a area, punching area, right? So the soil pressure is gonna punch through your foundation again in combine the footing as well, and we need to calculate this area, right? Outside of column, this area, isn't it? I mean this area, right? Okay, this area. This is a column, and this is a critical section, okay, in this area. So, and anything else, same. So if we have a interior columns, exterior columns, and corner columns, you can decide and pick up the number for 40 for interior, all right? And this, you're gonna choose one of them, actually depending on better. And I'm not gonna go through all the detail again. You can take a look at three foundation video clips, and also you can take a look at the uh, structural analysis course, and also this has been discussed a slab in reinforced concrete, right? Okay, and here we're going a little bit force caused by eccentricities, and this is nothing but a real small calculation to make sure that you're okay from shear eccentricity around the columns. Okay, you can follow the calculations here. All right, and this example can be very long if you have to consider design against a unbalanced moment acting on the slab, and we are familiar with this unbalanced moment as we learned from slab design. You want to go back and review slab designs where how we treated the unbalanced moment, and I just go briefly review that part in column perspectives. All right, so what is the unbalanced moment? Unbalanced moment on foundation, especially in combined footing, are calculated with respect to a shear center of shear parameters right here, center of shear parameters right there. So we have a column load coming down, we have a soil load coming up, so we can calculate a unbalanced moment acting on this part of the slab at this particular columns, right? And this is how somehow we have to treat this unbalanced moment by levers and by concrete of the foundation. Okay, this is how we're going to treat the unbalanced moment and how to calculate unbalanced moment, right? So we'll assume that we just take a look at all these dimensions. Our dimensions are very easy, and this is a center of a shear center, calculating this from a axis of loading, and this area, this distance is from axis of a shear flow bearing pressures and all that. So we come up with a unbalanced moment with this right here, 851.9 kilonewton per meter, all right? And here we have to calculate a polar moment of inertia. Okay, so polar moment of inertias are calculated with the three cases, one in the middle, one in the corner, one in the edge, and we calculate Ix and Iy and come up with a polar moment of inertias. And there are detailed in slab section. If you take a look at my lecture note on slab, or you can go back to any books for slab design study at polar moment of inertia to come up with this. And this is our number. So you can just easily follow these numbers from our little dimensions over there, configurations and dimensions over there, with respect to the shear center of shear parameters. Okay, and we have this JC. Now you're going to calculate one more thing, which is gamma F. The gamma F is the portion of the moment that must be resisted by the levers. Okay, this is percentage. And B1 and B2 is the dimension of the column depending on the axis of moment. And this is quite a bit a very important formula in understanding the unbalanced moment and how to design against that unbalanced moment, right? So 66.5% should be resisted by a lever, fracture levers, and the rest should be resisted by the shear force and shear strength of the foundation. Okay, this is a formula, very famous formula for shear. This is U, the shear force, the shear stress. I mean, okay, this is a vertical shear, and this is shear to unbalance the moment, right? And this much portion must be resisted by the shear capacity, and the rest of them should be resisted by the levers, fracture levers, right? So now this is a shear unbalance, shear and this portion only, okay, at 33.5, right? And now the shear stress calculated as 1.52 megapascal. And look at you calculating your shear capacity and design shear capacity from nominal shear capacity when you use a phi factor. Similarly, we calculate this. All right. Similarly, we calculate this, and we decide to take which value. Okay. This smallest value, right? So this is the smallest, right? Okay, so we're not okay. We're not okay, and unfortunately, we have to repeat all this lengthy calculation one more time until this design shear capacity is greater than shear stress, right? So maybe we have to do it again. Here we have to do it again. Then you can come up with a section where it can satisfy this equation, which the design shear capacity is greater than shear stresses or load, whatever. Okay, so this is a equation that looks a little bit unfamiliar right now. Then it's okay. You go back to slab design, take a look at a review like 20 minutes, 30 minutes, and you should be able to recall what's going on with the treatment on how to take care of unbalanced moment, all right? And this is gonna be the last example, but combined foundation design is not that simple, is it? Because it can be very lengthy depending on the details. And also we have to take care of all the connection details. I'm not gonna go through here, but you can follow that I gave you in previous video clips to design the dowel bars and all the details in connections and splice lengths between dowels and column reverse, whatever. Okay. This could be quite lengthy, but you should follow these procedures to design a good foundation. So by today, we have learned a shallow foundations. I think we covered almost all shallow foundation except for a mat foundations. The mat foundation is the foundation you want to really get familiar with for high-rise building design for big buildings, right? So we're going to have to hold on to get into the mat foundation or raft foundations. We're going to go to pile design first, deep foundations, and with the pile caps before we go back to the mat foundation and raft foundation in next video clip. So we're going to probably spend 1 or 2 video clips for discussing a deep foundations, which is pile foundations. And pile foundations also ask you to take care of a pile cap, which is similar to shallow foundations. Okay, if you see, go there, and this is a configuration of the deep foundation. You have piles over there. But you need to have another big shallow type of foundation, which is called a pile cap. This is cap, right, under the pile. So this is called a pile cap, and this pile cap design is exactly same as what we have learned and discussed with the shallow foundation. That is why I want to go back to this deep foundation first and design not only the deep piles but also a pile